So that concludes the ionization portion of the how mass spectrometry works part of this lecture. We move on to mass selection, or the mass analyzer, next. Since there's still at least maybe 15 minutes of time left before I'll stop, I'm going to just keep going. And then around, by my clock, 10:55, I'll take a break and see if there's any questions before I wrap up. Okay, so there are many types of mass analyzers, or also known as mass spectrometers. I'm going to go through as many as I can with you, and there's more than I give here as examples. I'm just giving you some of the more common, well-known ones. So there are magnetic sector mass analyzers, quadruple mass analyzers, time-of-flight mass analyzers, ion traps, orbitrap mass analyzers, and ion mobility mass analyzers. So let's start with the magnetic sector. This is historically one of the first mass analyzers created and has been in use for a very long time. It is a cool continuous mass spectrometer. I'll tell you what that means in a moment. And as the name implies, this mass analyzer uses a magnetic field to separate ions. I actually kind of flubbed earlier when I said we move ions with applied voltages. We can also move ions with applied magnetic fields. There's still a high voltage that's applied to the ions to accelerate them into the magnetic sector, but the actual separation and filtration in a magnetic sector occurs with a magnetic field. Now, a continuous ion source is generated and supplied from the ionization unit to the magnetic sector. So that means that there's a constant voltage and it's continuous that goes from the source to the sector. And so you kind of have to have a fair amount of sample to use this particular type of instrument and have it going through sort of constantly for a while. And when the ions enter, they are then exposed to the magnetic field. And as a result, the ions are deflected according to what's called Fleming's left-hand rule. If you remember Fleming's left-hand rule, that's where you figure out the direction of the magnetic field based on your thumb when you put your hand into a sort of fist with your thumb pointing out. I learned that in first year, I think physics or something like that. So I hope most of you learned that too. All right, so there's something called a Lorentz force that goes in one direction and the centrifugal force in another, because you're actually bending these ions. They bend when they go through a field. It's very much like light passing through a prism. And based on how far the ions are deflected or not, you can determine what the original mass to charge ratio would be. And so something that has a larger mass may not deflect as much as something that's a smaller mass. Smaller mass would have a larger theoretical charge density and therefore maybe get bent by the applied magnetic field in a stronger way. So what's great about magnetic sector mass analyzers is they are very high resolution. So you can resolve isotopes using magnetic sector mass analyzers. Isotopes of metal atoms and very small mass differences. And you've also got a very high dynamic range. So you can measure anything from 10 to 10,000 Daltons in size. And these interface best with gas chromatography systems. This does not work well with liquid introduction. And they're huge. I don't know if I show a picture. No, I don't. Just so you know, these instruments tend to take up a lot of space, especially if they're very high resolution. I mean, there are small ones I've seen that are little, like almost the size of a printer, like a little desktop printer, and they separate carbon and nitrogen. But if you're going to go and try to separate iron or mercury or high molecular weight atoms, not molecular weight, sorry, high atomic weight masses, then you would want one of the larger systems that can almost be the size of a desk or a room. Okay. So quadruple mass analyzers are one of the most common mass analyzers. So we have a QTOF, which has a quadruple Q and then time of flight, which is the other. So that's a tandem mass spectrometer. Quadruple mass analyzers are pretty cool. They are exactly what their name says. There are 4 poles that are oriented in such a way that you can change the applied voltage on each pole. It's always sort of opposite. So you've got a negative and a positive, and they alternate and flip back and forth. And as you alternate them and change the intensity of that applied voltage, you move the ions through those 4 poles like a filter. When the masses are too big or too small, they will hit the poles and get knocked out of the mass filter, the mass analyzer. And when they are exactly what you're looking for, they fly through in this beautiful wave-like motion, and then they hit the ion detector. Let's see. So it's a hyperboloidal, that's it, interior surface. That's what they call that. So it's like a hyperbolic chamber on the inside, I guess. And so this is a direct current, high frequency, radio frequency style mass that goes on in here. And so like I said, as these change in their voltage and location, that's where you get the frequency, and the direct current is constant current that's applied across these poles. And they are first accelerated, or the goal is to accelerate them in the Z direction with a relatively weak voltage. And then they get through this tiny hole at the very end. So usually, like I said, the same type of voltage is applied obliquely opposite or diagonally on the opposite poles. And the combination of the direct voltage and frequency causes these things to move. All right, I already explained that in the first place, and that's what all the little points say. Now, the quadruple mass analyzer, visualized in a different way. So you have your ions going into the mass spectrometer. You can do a sort of scan mode or a sim mode. So for a scan mode, you start with a low voltage and you increase it over time. And this causes the mass filter to select different ions throughout the process. And it's at the end of the analyzer, the ion detector is detecting each one of these over time. So it sort of accumulates the total of all of these different ions over that time period. And it's called a scan. And so your mass spectrum will contain all of those different ions. But you can also put it into selective ion monitoring mode or SIM mode. So here you select for one particular ion, the voltage is set, it's constant, and you wait for a certain amount of time for enough ions to accumulate at the detector that you can get a good mass spectrum. So one of the best things about quadruples is that they're very fast and they usually are very sensitive. Their mass ranges are okay, usually up to 2000 mass to charge ratio. They also allow for high speed polarity switching, which means that you can, like we describe here, monitor multiple selected ions at once and do a scan mode. And this can deliver a very high sensitivity quantitative analysis for many target compounds at once because they're so quick. So it's very useful in tandem mass spectrometry, which I'm going to explain soon, where you can set them up together in tandem, and your first mass analyzer is a quadruple. Sometimes your second mass analyzer is a quadruple as well, or a different mass analyzer. But that first one basically just acts like a really cool filter that can do all this scanning and selecting for you. And then the second mass analyzer can maybe give you some extra features that you can't get with a quadruple. So I'm not talking about the features here, but one of the things that quadruple mass analyzers aren't good for is high resolution. So they can't necessarily separate very similar, two molecules that are similar in mass. One variation of a quadruple mass analyzer is called a hexapole. It has 6 poles. Usually there's a hexapole in every mass spectrometer that just, it's small and it's used for guiding ions. They tend to use this just to move ions through the system, not necessarily as a selector or a filter. Okay, now the time-of-flight mass spectrometer. This one is one of my favorites. This is a pulsed and non-scanning mass spectrometer, as they call this. There's a simple construction consisting of an accelerator, a reflectron, and detector inside this high vacuum chamber, which is called a flight tube. The longer your flight tube, the longer your flight path, and therefore the better resolution you have. So over time, these time-of-flight mass spectrometers have gotten taller and taller in their flight tubes. This detects ions by measuring the time it takes for the ions to travel through the flight tube, hence its name, time of flight. Ions are accumulated and introduced in pulses. So like it's literally called a pulsar. So if you have, for instance, a mass analyzer ahead of your TOF, like a quadruple, you could have the quadruple select or scan, and then there's a little cell that collects, that allows the ions to sort of just accumulate in it, and then the pulsar pushes them all out at once. It's sort of like the start of a race of runners where what's that called? The starting pistol fires. And that's when you go, your pusher is your starting pistol, and you want to make sure all your ions start moving through the flight tube at the exact same time. And that's probably the most important thing to make sure you get right with one of these, because then that determines the time at which it's going to hit the detector. Like I said, the longer the flight tube, the better the resolution. So the more separation you can get. So if you have two ions that are very similar in mass, you can start resolving them with a longer tube. And then there's this thing at the bottom called a reflectron. So if your tube is 4 feet long, because of the reflectron, you basically get a flight path of 8 feet. There are some that do this weird W reflectron pattern, but those weren't very effective. So I think that most now just have this one reflectron process. And ions that are smaller tend to take less time to reach the detector versus larger ions that take a little bit longer to reach the detector. So it's kind of similar to a magnetic sector that way, because the smaller ions get to the detector first. The features here is that it's actually pretty high resolution. So you can resolve molecules up to 30,000 parts per billion in difference. So what that actually translates to is 0.0001 mass units can be resolved from each other very easily. In fact, less, 0.0001. It's also pulsed, and you got really fast. So these ions travel through the flight tube in milliseconds. It is so fast. All right. I've got just a couple more minutes, so I'll do Fourier transform ion cyclotron resonance, FTICR, and then take a pause, and we'll end here for today and then start back next week. This is based on the cyclotron frequency of the ions in a fixed magnetic field. And you're like, what's the cyclotron frequency? Okay, well, probably best illustrated, actually. So there's sort of this thing called a penning trap, where you have a north and south sort of magnet, and some plates that have a radio frequency applied with I guess an ammeter. I'm not sure what. Anyway, you apply this wattage, amperes, and your ions are going to make this sort of cyclic path, which is the cyclotron frequency. And this is called a penning trap. So as you excite these ions based on their sort of resonant cyclotron frequencies, they are going to spin at a sort of different frequency. And then once you remove this excitation field here, the ions are then rotating at their basic frequency in a packet. And then the ions can induce a charge, which then sort of looks like an image current on the pair of electrodes. And the resulting signal is called a free induction decay, or FID, transient or interferogram. So really, we're talking about sine waves. So you end up having these things moving based on this sort of magnetic field. And then you can measure their frequency, and depending on their mass, they're going to have different frequencies of orbit. And then your output sort of technically that's getting detected is frequencies. Then in order to read that signal, because it's very complex and very cyclical, you use Fourier transform math to transform that into a mass spectra. So this mass spectrometer, which I know very little about, and you can probably tell because my explanation of it isn't nearly as, I'd say, sophisticated as the other ones, is that you get a super high resolution separation. So you can resolve very large or very molecules that are very similar in size. And it's also huge. This is as big as a magnetic sector instrument or larger. And for the higher the resolution, the bigger these things get. Ion trap mass spectrometers, there's only one thing that's come up now. So we're all together. We're all on track. So this is a pulsed quadruple. And the poles aren't as obvious as in the quadruple I showed you before. They're actually arranged in different sort of electrode, kind of like a case. It almost looks like a ball or a little box. So here you have ring electrodes and end cap electrodes. And what happens is the ions travel through slits on the sides of these end cap electrodes. And so these are your 4 poles, but they're not literally poles any longer. They're shaped in a different way. And there is a cooling collisionally induced dissociation gas that can travel in here, and you can do just collisional, you can fragment your ions in here. But basically, because of configuration of an ion trap, the ions oscillate in there in sort of like a ball sort of pattern or pathway. So the ions will come through in a pulse, sort of come in pulses, which is actually kind of similar to the way the QTOF works, where ions are pushed through the time of flight mass spectrometer by the pulsar or the pusher. And then the ions get trapped inside this sort of box. So that's why it's called an ion trap, because they're actually trapped in there. And then ions and this is a very temporary, very short-lived thing. So this happens in milliseconds or microseconds even. And the ions with varying masses will experience different oscillations. So every sort of mass group will travel together in one oscillation, and a different set of masses will travel in a different oscillation. And it's by sort of modulating that with the applied voltages on the electrodes, you can change the shape of those oscillations, and you can intentionally select certain ions, and you can knock other ions out by having them hit the walls of the trap. So that's sort of what I've described here, but here you can sort of see it as an image. So let's say you want to adjust the oscillation of the target ion you're looking for, and in this diagram it's blue. So you do this so that it is intentionally unstable and travels through the slit, and you usually have the detector right at the other end of the slit. But you can also intentionally knock things out or have them hit the walls of the quadruple ion trap, and then they no longer are oscillating. And that's also how you can select for a set of masses and then push them through into the rest of the mass spec or towards the detector. All right, so the ion trap is sort of the simplistic and original version of what we now have, which is called an orbitrap. An orbitrap is definitely one of the top of the line mass spectrometers. If you know anyone who does mass spectrometry, you'll know they refer to these as Orbies. Ev has one at Environment Canada. So this is the evolution of the ion trap mass spectrometer. I was really lucky when I was at Trent to work with a man named Ray Marsh, by the way, who is one of the grandfathers of mass spectrometry, and he patented and invented the original ion trap mass spectrometer. And so now the orbitrap is an evolution of that. And instead of a ring electrode, there's an inner elliptical electrode, which is so cool looking, right? And the ions get trapped because of their electrostatic attraction to the inner electrode, and they travel around the electrode. And this gets balanced by their inertia. And as the ions cycle around that electrode, they make these cool sort of elliptical trajectories, and you can move them back and forth along the axes. You can collect them and basically trap more and more ions of the same mass to charge ratio and build up a pretty decent signal. So in a way, orbitraps are very sensitive because you can just trap more and more ions that you want, and and it's very elegant and sensitive. You can then, as you have them travel along this axis, and of course, none of you will ever operate a mass spec and have to do the math to figure out how to make ions move. That's all done for you now. Now you're just adjusting settings, but this is so that you understand what's going on the inside of each kind of mass spec you have. It's complex math. I can't do it. I've tried. Ray March used to teach it, and I failed miserably doing the calculus portion of his exams. Anyhow, so the central electrode, sort of the way their trajectories go around that resemble helices, right? So there's sort of this helical movement more so than the elliptical packets that were in the ion trap. So these mass spectrometers are also very high resolution. So you can separate very small ions with very small mass differences. So they're as powerful or more powerful than a QTOF for resolving very similar masses. And it's very precise and very accurate. So that's the company that has really cornered the market on the Orbitrap is Thermo Fisher Scientific, but I don't think you can get an Orbi from anyone else. So the Q Exactive is sort of the standard model that everyone looks for an Orbitrap, and there are different varying degrees of how powerful these ones can be, but a lot of people in proteomics like these Q Exactives. All right. So now another type of mass spectrometry, which is my new favorite and something I'm trying to get, is called ion mobility. All right, so in ion mobility, the ions will enter what's called a drift tube. And the drift tube is sort of like a concentric or a series of concentric focused rings that are actually electrodes. So they're ring electrodes. And the ions travel through here, and then in the opposing direction, so the electric field travels along here, and you can apply different voltages along that sort of set of rings. And they can focus and separate your ions. But what improves this dramatically is something called drift gas that travels in the opposite direction, which sort of creates a bit of friction or an opposing force for those ions. And it helps to get better resolution. So this is another pulsed mass spectrometer. It's also a trap mass spectrometer. So again, this would sort of be the evolution from an ion trap to an Orbitrap to an ion mobility. You can see here, instead of having your ions trapped and oscillating, you have your ions trapped but fighting against this drift gas and getting resolved as they travel through. It almost feels like gas chromatography in a way, but it's totally different. So they sometimes call this a drift tube or a drift cell, the thing that makes those the ion mobility mass spectrometer. And so there is a new dimension when you're measuring ions in an ion mobility mass spectrometer. So we've always had the dimension of mass and charge. And you would have, if you're doing tandem mass spectrometry, you could have mass to charge of the fragment ions. You would also have retention time if you have a GC or an LC hooked up as at the beginning as a sample introduction system for your mass spec. So there's lots of dimensions so that you can, differentiate between two similar ions with all of that information. But the cool thing about ion mobility is it gives you one more, and it's called drift time. So drift time can then be converted into a parameter called the collisional cross-section. The collisional cross-section, if you really want to think about it, is actually a measure of the size of the packets of ions. And it is so remarkable that you can really resolve isomers, so two seriously identical ions, but just have slightly different shapes, will still get resolved here because their drift gas or drift time is going to be slightly different because they're going to form a different packet and a different shape. This is about as best as I can do to explain it. The math is much more complex. Like I said, it's really way over my head, and I'm just learning about it, but I just know ion mobility mass spectrometry is the shit. So this is really good for non-targeted mass spectrometry because it gives you one more level of information. If you have a really complex mixture with hundreds or thousands of molecules in it, be them proteins or contaminants or metabolites, this gives you one more level of identifying information so you can differentiate two very similar things. All right, so here are some other ways of looking at this. So you have your drift cell and you have the same molecule, but just in slightly different conformations going through the drift cell, and you will see them having different drift times. So if you add the LC or elution time or retention time, you also have your ion mobility drift time, and then you'll still have your mass to charge ratio. You have an extra dimension of data, and you'll get to see your mass spectra in all of these different dimensions when you do ion mobility. I worked with one of these. It was really cool at the Ontario Ministry of Environment, Conservation and Parks when I was looking at contaminants in dust from e-waste facilities, and it was really fun, the number of charts and graphs you can make. At a certain point, it's pretty meaningless though. It just like looks cool. But you can definitely resolve slightly different molecules, things that have the exact same formula, but maybe chlorine atoms on a slightly different part of a benzene ring, for instance, and it's really well resolved. Okay, so there are actually a few different types of ion mobility mass spectrometry. So there's drift time ion mobility mass spectrometry, where the ions drift through the tube and smaller ions will travel faster through the drift tube than ions with larger molecular weight. So this is sort of what I just showed you. Ions get separated based on their drift time, and drift tube ion mobility does not employ radio frequency voltage, which can heat ions, and therefore it preserves the structure of the ions. It leaves everything about their conformations intact. Then there's another type of ion mobility called traveling wave ion mobility spectrometry. Here, the ions are separating according to their drift time, but they travel in a wave, so they actually get a longer drift time through the same length because their path is longer. And so there are both radio frequency and direct currents applied to this drift cell, to the rings. And so it's oscillating more like you would oscillate in a quadruple or other type, similar type of mass spec, where you can adjust, and so you apply a different sort of frequency as opposed to just one voltage. It's constantly moving in order to create that traveling wave. And then based on the speed and magnitude of that traveling wave, you can separate your ions, and you can do it with much more purpose. You can actually select with this. And again, smaller ions will have higher mobility due to less collisions with the gas, and they exit the cell faster. But they come out, their actual readings, so compared to drift time, where you sort of have a linear progression of ions coming out of the cell, with their drift length, you're going to see more of a wave shape signal from the traveling wave. All right, then there's trapped ion mobility spectrometry. So here, the trap is shaped in a different way, sort of like a funnel. And so in addition to the traditional drag of the gas flow, you also lower the electrical forces. So in fact, the ions come out in a slightly different way. So this is opposite to DT IMS. So basically, I think the larger molecules come out first, and then the smaller ones come out at the end. It doesn't say that there, but I should say that more explicitly. And then in the differential mobility spectrometry version of ion mobility, which is also known as field asymmetric waveform ion mobility spectrometry, or FAMES. Here you have radio frequency, direct current, ion mobility spectrometry that sort of it's sort of like a version of the traveling wave where you're doing isoscillation. Is that the right word? No. Anyway, you're oscillating your frequencies, and you intentionally knock things into the walls of the drift tube so that you can select the ions you're looking for. So it's more of a selective process as well. So depending on the ratio of the high field and low field, it'll migrate either towards the electro, which is the sides of the tube, or straight through to the detector. It is also really well known that the high radio frequency distorts the conformation of the ions. So the collisional cross-section element gets lost. So you can no longer measure the CCS of the ions. So this has a different purpose maybe than the other types of ion mobility mass spectrometry devices. All right, so those are the different types of mass spectrometers that most people use, and I could go on and on about some other ones, but that gives you sort of the quick overview. Now I'm going to go over a few more concepts and definitions. So mass accuracy, you'll hear people use this term a lot. This is the relative difference in the measured mass and the exact or true mass of an ion or a molecule. And in order to determine the mass accuracy of your instrument, you have to calibrate and run standards and figure this out. So basically, if the true mass of the ion is here, and this is what you've measured, the accuracy is a measure of the difference between those two. And it is usually affected by the resolution of the instrument. And so sometimes if the resolution is really poor, you can't resolve two different masses, and therefore the true mass and the measured mass get obscured, and you don't have a really good way of determining how close you are to the true mass. There is an equation for this, and it's pretty straightforward. It's the mass measured minus the mass, the true mass, over the true mass times 10 to the 6th. And we usually report this as a ppm measurement. So you hear a lot of people talking about, they won't even say mass accuracy. They'll just say my mass spec or my measurements were at blah, blah, blah ppm. And you might be kind of scratching your head because it's sort of a parts per million measurement because you multiply by a million, but it's not the same as, say, a concentration ppm because there's a difference implied in there. Okay. Resolution. This is the resolving power, and it's defined as the mass over the difference in mass, I think. So that's the peak width necessary for separation at that particular mass. So really here, this is very similar to concepts in resolution for anything else, like a microscope or any other sort of detector where you have to resolve two things. And so even like in chromatography, we talk about resolution as well, and it's the same idea, where two peaks are fully resolved if you can measure the distance between them. And usually we use the 10% valley or 50% valley, which is also considered full width at half maximum sort of measurement to report the type of resolution of your mass spec, or the way trying to figure out what the resolution would be. Resolving power is usually a large number. So the bigger the resolving power, the better the resolution of the instrument. So it's usually used as a performance parameter. So when you're going to buy a mass spec, if resolution is important to you, you'll be looking at those numbers. The mass specs get exponentially more expensive the more resolution they have, and sensitivity is somewhat often kind of not as good the higher you go up in resolution, but really powerful mass specs can do both very well, and they're very expensive, in the millions of dollars range. So let's compare the mass analyzers based on the definitions I just gave you. So the magnetic sector instrument that I started out with, the original grandfather mass spec, it's sort of a gendered term. I should come up with something better. The grandparent mass spectrometer. That's better. You have your mass accuracy of 1 to 2 parts per million. And then your resolving power can be up to 100,000. So we've got some really high resolution power with a magnetic sector. That's why it's often applied to things that have very subtle differences in mass, like isotopes. So you can measure isotope ratios. And with this particular type of mass spec, which I mentioned before, it can only be coupled to a GC, which is a gas chromatography introduction system. You can also just do direct infusions with these, but you can't do LC. Quadruple ion time of flight mass spectrometers have a larger ppm, which means that they are less sort of accurate. They can be less accurate, but they have as well a lower resolving power. However, they're fast. They're known to be very fast. They're very good for scanning, and they're often used when you're doing tandem mass spectrometry, where the first filter is your quadruple or ion trap mass spectrometer. Time of flight mass spectrometers have a much better mass accuracy, closer to that of a magnetic sector, but not quite as good, and a pretty decent resolving power. This is what we are looking for when we tune the QTOF, which right now I'm doing. And the target, the best, is usually 30,000, but in reality, usually range between 20 and 30,000, depending on the ion in the system. This is the kind of resolution we need for larger molecules like proteins and oligonucleotides that are very similar in mass. These mass specs are scanning with pulse, and they're very good for non-targeted, and they're relatively fast, but not nearly as fast as a quadruple. Now, the Orbitrap has fantastic mass accuracy. It rivals or betters magnetic sectors. The resolving power is equal to that of the power of a magnetic sector. This is a pulse trap with very high resolution, as well as very high sensitivity. The very best Q exactive on the market that I got a quote for about 3 or 4 years ago now, so it's probably worth more, is about $1.5 million. And then the FT ICR, the Fourier transform ion cyclotron resonance models, have even better mass accuracy and even higher resolving power, but they're huge. They can only be coupled to a GC. They are the best for looking at really small particles. These are used to look at dark matter and CERN, and they're really cool. And there are a few around. And if you want to get the most powerful ones, they're really expensive, just like the Orbi. And then there are these new ion mobility mass spectrometers that I'm so fond of. They have amazing max accuracy, especially if you can include the CCS. The resolving power isn't quite as great, but they're really good for getting that additional measurement, and they're also excellent for non-targeted mass spectrometry applications because of that. They can be coupled to LCs or GCs.